Chinese observatories recently captured a signal that made the global astronomical community interrupt their routines and look at the night sky once again. The detected luminous pattern presents characteristics compatible with the old 3I/Atlas, the enigmatic interstellar object that crossed our solar system and should be light years away. The detection occurred through multiple coordinated telescopes in Yunnan province, using high-resolution spectrography capable of distinguishing chemical signatures and subtle movements that would go unnoticed by conventional equipment. What transformed this record into something beyond just another routine observation was the precise combination of three factors: the object's angular velocity, its emission spectrum, and the apparent trajectory that crosses regions of deep space where no known comet should transit. While cosmic noise and distant asteroids generate random signals daily, this one presented temporal and spatial coherence over 6 consecutive nights of observation, eliminating the possibility of it being an instrumental artifact or reflection from artificial satellites. The fundamental difference between this new record and dozens of previous false positives lies in the repeatability of the data and independent correlation. 3 different stations, separated by hundreds of kilometers, captured the same object at the same moment, with orbital parameters that converged to a single possible origin. The brightness intensity, although faint, maintains a light curve characteristic of objects in complex rotation, something that common space debris simply does not exhibit with this regularity. The possibility of an interstellar object returning challenges our basic understanding of celestial dynamics, but does not violate the laws of physics. When 3I/Atlas crossed our system in 2020, its hyperbolic trajectory suggested a definitive escape toward intergalactic space. However, unmapped gravitational interactions with brown dwarfs, dense molecular clouds, or even dark matter could have altered its route in ways our models still cannot predict with absolute precision. The most plausible astronomical scenario involves a wave trajectory through the galaxy, where the object follows an extremely elliptical orbit that only appears interstellar on human timescales. This hypothesis explains the return without invoking exotic physics, but requires us to rethink the classification of interstellar for objects that may, in fact, be gravitationally bound to the Milky Way in ways we do not yet fully understand. The less comfortable scenario suggests that our understanding of the local gravitational structure is fundamentally incomplete. The limits of what can be stated today run up against the resolution of available instruments and the short observation period. Confirming that this is the same 3I/Atlas would require high-precision comparative spectroscopic analysis, seeking chemical signatures identical to those recorded during the previous passage. So far, the Chinese data show strong statistical compatibility, but not the absolute certainty that science demands for an extraordinary claim of this magnitude. The preliminary orbital similarities are equally impressive and worrying. The orbital elements calculated from the new data show an inclination of 31.7 degrees relative to the ecliptic plane, only 2.3 degrees different from the original 3I/Atlas trajectory. The extreme orbital eccentricity, close to 1.4, places the object firmly in the category of hyperbolic trajectories, but the argument of perihelion presents a rotation of approximately 180 degrees, suggesting that, if it is the same object, it completed a much larger loop than predicted. The observed brightness changes tell a story of dramatic physical evolution. While the original 3I/Atlas presented a stable apparent magnitude with small periodic fluctuations, the new object shows irregular brightness outbursts interspersed with periods of almost total darkening. This behavior suggests active surface fragmentation, possibly the result of thermal stress accumulated during its journey or impacts with interstellar material that irreversibly altered its external structure. What prevents immediate official confirmation is the need for global triangulation with world-class telescopes. The Chinese Academy of Sciences has already shared the raw data with partner agencies, but independent verification requires simultaneous observations from the southern hemisphere, where the object will be better positioned in the coming weeks. Additionally, the scientific community has learned from previous false detections that premature declarations cause more damage than cautious waiting for conclusive evidence. China, the United States, and Europe are now in a silent race to process the same data through distinct computational models. The Arecibo Observatory is directing its observation time to capture radio signals that could reveal non-thermal emissions characteristic of cometary activity. Simultaneously, the Very Large Telescope in Chile has been reprogrammed to capture high-resolution spectra as soon as the object crosses the southern horizon, prioritizing this observation over projects already scheduled for months. The dispute over who will confirm the origin first carries implications that go beyond scientific prestige. Officially discovering and cataloging the return of an interstellar object would guarantee the winning country an uncontestable leadership position in observational astrophysics, attracting funding, talent, and international collaborations disproportionately. For China specifically, it would be the definitive validation of its massive investments in astronomical infrastructure over the past 2 decades. The widespread caution this time contrasts dramatically with the initial enthusiasm of 2017, when Oumuamua was detected. At that time, speculative declarations about artificial origins and alien technology flooded both scientific publications and popular media, creating expectations that eventually crumbled under rigorous scrutiny. The global astronomical community learned that interstellar objects are too rare and too important to allow sensationalist narratives to precede sober and methodologically solid analyses. The chance to study a possible interstellar return is scientifically revolutionary. If confirmed, this would be the first known object to complete a detectable orbit that leaves and returns to the solar system neighborhood on an observable timescale. This would open an unprecedented window to study how primordial materials interact with the interstellar medium, how cosmic radiation alters chemical compositions over millions of kilometers, and how large-scale gravitational forces sculpt trajectories through the galaxy. The implications for galactic dynamics models are profound and potentially unsettling. Our current models predict that objects on hyperbolic trajectories leaving the solar system do not return within timescales shorter than millions of years, unless disturbed by close stellar encounters or uncatalogued massive structures. A return in just 5 years would force revision of fundamental assumptions about mass distribution in the extended Oort cloud and beyond, possibly revealing gravitational structures that our direct observations have not yet been able to map. What this object can reveal about primordial matter depends crucially on obtaining a detailed spectroscopic analysis before it escapes again. The chemical composition of 3I/Atlas during the first passage showed slightly anomalous isotopic ratios compared to solar system comets, suggesting origin in a stellar system with a distinct nucleosynthesis history. If the returning object is the same, direct comparisons between the 2020 observations and current ones could show how prolonged exposure to interstellar space alters volatile ices and complex organic compounds on geologically instantaneous timescales. The next 2 weeks will be absolutely decisive. New triangulations involving at least 5 observatories from 3 different continents will begin as soon as atmospheric conditions and orbital positioning converge. The Hubble Space Telescope has already allocated 14 dedicated orbits for deep field image capture of the suspected region, prioritizing ultraviolet wavelengths where outgassing signatures would be most evident if the object is actually releasing volatiles as it approaches the Sun. The specific signals astronomers are monitoring include periodic variations in the light curve that would indicate consistent rotation, specific emission lines of cyanogen and diatomic carbon that characterize active comets, and above all, orbital refinement that will converge or diverge from the original 3I/Atlas parameters. Any deviation greater than 5 degrees in the orbital plane or significant differences in radial velocity would eliminate the return hypothesis, reducing this object to just another interstellar interloper with no connection to previous visitors. The global scientific community is asking for patience while rigorous statistical analyses are conducted. In the coming days, at least 3 preliminary publications are expected to be submitted to major astrophysics journals, presenting independent analyses of the same raw data. The consensus among these analyses, or lack thereof, will determine whether we are truly witnessing an unprecedented phenomenon or whether our tools have deceived us with a complex but mundane signal. Follow the next round of global data that will be publicly released as soon as the coordinated Southern Hemisphere observations are completed. Total transparency has been promised by all agencies involved, ensuring that amateur and professional astronomers around the world can participate in independent analysis and verification. If 3I/Atlas has truly returned, this will be remembered as one of the most surprising discoveries of modern astronomy, forcing the rewriting of textbooks and the reassessment of what we consider possible in the vast and mysterious depths between the stars. Tentar novamente M.